the most important reaction of carboxylic acid esters, both in commercial processes and in the body, involves the breaking of the ester linkage. Now, this process can either be called ester hydrolysis or saponification, depending on the reaction conditions. And the first thing we're going to look at is ester hydrolysis. Ester hydrolysis is the reaction of an ester with water to break that ester linkage, and it produces an alcohol and a carboxylic acid. This process is just simply the reverse of the esterification reaction, and strong acids are frequently used to catalyze as catalysts to hydrolyze the esters. So when we look at this particular reaction, we take the ester here, we add water and an acid, which we're going to represent as H+. We end up with a carboxylic acid and the alcohol. It's sort of like if we take and cut it right here. This part is the alcohol, right, with the R prime, and then this part is the carboxylic acid with the carbonyl group. Now, the human body and other biological organisms are constantly forming and hydrolyzing a variety of esters. And the catalysts in these processes are protein catalysts called enzymes, which we're going to get to in chapter 20. Animal and vegetable oils are esters. And their enzyme catalyzed hydrolysis is a really important process that takes place when they're digested. Now, I want us to look at a few other examples of ester hydrolysis and specific examples. So, we have our ester there, and we are going to react it with water. And we are going to try to predict the product here. When we go and predict the product, my suggestion is to draw a line right here in between your carbonyl carbon and the oxygen. Everything here is going to go and make your carboxylic acid. So then we can come over here and say we have CH3, C double bond O, OH, and that's our carboxylic acid. And then everything to this side is going to make your alcohol. And so that gives us, and you just make the alcohol by putting the hydrogen on the oxygen. Now, let's do another example. All right, so we have an example. It's got a ring, but we're not going to panic about it because we're going to find our ester bond and we're going to draw a line just like that. And we know that this makes up our carboxylic acid, and then this part is going to make up our alcohol. And so when we come over here, there's our carboxylic acid. And then we just add an H onto the oxygen to make our alcohol group. Now, let's look at saponification. Saponification, like ester hydrolysis, results in the breaking of an ester linkage, and it's also going to produce an alcohol and carboxylic acid. However, unlike ester hydrolysis, saponification is done in solutions containing strong bases like potassium and sodium hydroxide. So the previous reaction we used an acid, and now we're going to use a base. We use a base because in this particular reaction, the carboxylic acid is then converted to a salt. So, for example, if we start out here with our ester again, and we're just looking at a generic ester here, and we are going to add potassium hydroxide, and that is a strong base, but it could also be sodium hydroxide as well. So one of our strong bases, and we are going to form a carboxylic acid salt. Where, oh, I used the wrong counter ion. I was looking up there at that sodium. Where with our salt, we have to do the potassium ion here, and it forms a +1 charge. And then we have this negative charge here, because what happens is we come in here, right, and everything to this side forms that salt, and then the R prime here goes on to the alcohol there. Okay, so that's what we see as far as our saponification reaction is concerned. Now, let's look at a specific example. So in our specific example, we're going to have methyl benzoate and we are going to react it with sodium hydroxide. When we do this, I draw a line right here, and I know that everything here is going to make my salt. And so I go ahead and I draw my salt, and then I look at the counter ion and go ahead and draw that counter ion in. Then I know that this and this are going to combine to make my alcohol. And so then I get methanol just right like that. So those are our two ester reactions that we're going to look at. At the end of this chapter, there's also a reaction map for carboxylic acids. When we learned about carboxylic acids at the beginning of the chapter, we know that we can react it with water and it'll dissociate, where the proton of the carboxylic acid will pop off and you'll get this O- here. And then if we add a base, we know we'll get a carboxylate salt. And that, for example, looks like that. Okay. If we react a carboxylic acid with an alcohol, and I want to remind you, carboxylic acid looks like this, then we get an ester. If we take that ester and we react it with a base, we get a carboxylic salt and an alcohol through saponification. And then if we react it with an acid, which is represented as H+ in water, we get carboxylic acid and an alcohol. So these, I feel like these reaction maps are incredibly helpful. Now, we need to look at one other type of ester. We have defined a carboxylic acid ester as the product of a reaction between a carboxylic acid and an alcohol. Alcohols can also form esters by reacting with inorganic acids like sulfuric, nitric, and phosphoric acids. The most important of these is phosphoric acid. And the reason it's the most important for us is that we are going to see it again in our biochemistry section. And so this chemistry is the same thing we've seen, where we have an alcohol, and then this is our phosphoric acid structure. And what happens is this proton and this OH group form the water, and then this group here is now this group here linked to this group here. Okay, and so now we have our phosphate ester. Now, I want you to notice phosphoric acid has 3 hydroxyl groups here, 3 OH groups. And because of that, it can form a mono di, and triester. When we talk about these biological phosphoric esters, mono and diesters are very important biologically. For example, if we look at glucose 6-phosphate, which is here, this is the first intermediate compound formed when glucose is oxidized to supply energy for the body. And at body pH, the two OH groups of phosphoric acid are ionized, and the phosphate group has a charge of -2. Okay, and the -2 charge comes from this oxygen here and this oxygen here. Now, when we talk about our phosphates, they can also form di and triphosphates. And when we look at this, this is a diphosphate ester, and this is a triphosphate ester. And a di here means you're going to have 2 phosphate groups that are linked together, and the tri here means you're going to have 3 phosphate groups that are linked together. Adenosine, diphosphate ADP, and adenosine triphosphate are 2 phosphoric anhydrides that are super important. And in this case, the R here is the adenosine. And as we study key compounds and the storage and transfer of chemical energy in living systems, we are going to encounter these phosphate esters in 2 or 3 phosphate groups where they're linked. And so it's really helpful to go ahead and recognize those. Specifically, and I want to show you the actual adenosine diphosphate, which is ADP. And then adenosine triphosphate, which is ATP. And these are the most important compounds. They're really the energy currency in the cell. So we are going to look at their structures a little bit more in detail later. So just for now, note that they've got ester linkages and the presence of the di and the triphosphate groups. And note again that at the pH that the body has, you're going to note that these are charged. So the charge for ADP is -3, the charge for ATP is -4. So for us, this ends chapter 15. In our next chapter, we are going to look at amines and amides. As always, if you have any questions, please feel free to pop by my office.